Hello, fellow quantum physicists. Today we are tackling the problem of the particle in the box, also known as the infinite square well, which consists in solving the Schrödinger equation for the following potential: Vx 0 between 0 and a, and plus infinity elsewhere. If we draw this potential, it would look like this. Here is a, here is 0, and outside of 0 and a, the potential is infinite, which means that the particle cannot exist there because the particle cannot have an infinite energy. So the only place where the particle can exist is in this region here. And the question we ask is how or what will be the behavior of the particle in this region? And this is exactly what we aim to investigate. To do that, we solve the Schrödinger equation, the time-independent Schrödinger equation, h psi equals e psi. And if we project this equation in position space, we have the kinetic term, minus h power squared over 2m d squared dx squared psi x, plus the potential term Vx psi x equals E psi x. And as we just said, the equation can only be solved in the interval 0 and a, because outside the potential is infinite and the particle does not live there. So between 0 and a, this equation simplifies to the following. The Vx is equal to 0. So we simply have this. And if we rewrite this a little bit, we have d squared dx squared and we can define some constant kappa in order to simplify the notation, so kappa squared, where kappa is equal to square root of 2me over h power squared. And this is the equation that we have to solve in order to find the wave function of the particle in the box, which will give us the behavior of the particle in this box, the allowed behavior of the particle in the box. So this is a very familiar differential equation of order 2 that we know can be solved with trigonometric functions. So we will look for a wave function of the form a cosine of kappa x plus b sine of kappa x. And now we use the fact that we know that the particle cannot live outside the interval 0a. So this means that the wave function will be 0 outside 0 and a. And in particular, we expect the wave function to be continuous at the points 0 and a. So this gives us the following boundary conditions. Psi 0 will be equal to psi a will be equal to 0. Let's see what it gives on the left boundary. It gives us a times cosine of 0, so 1, plus b times sine of 0, so 0. So a equals 0. Now, for the right boundary, we know that a is 0, so we don't have to write it, plus b sine kappa a is equal to 0. So now, what does this tell us? It tells us that sine kappa a must be 0 because b cannot be 0, otherwise a and b are both 0, which would mean that the wave function is also 0 in this region. But we know that it's not 0. So b cannot be 0. Therefore, it is the sine of kappa a which is 0. And what does this tell us? It tells us that this kappa, or this square root of 2me over h bar squared, it has to have values that are in accordance to this constraint here, this sine kappa a equal to 0. Therefore, for the particle to exist in the box, it has to verify some constraints on its energy. There are some constraints on the energies that the particle can have. So let's solve for the possible energies that the particle can have by solving sine of kappa a equals 0. So if you remember the trigonometric circle, so the sine is on this axis and it's 0 whenever we are either here or here. So this means that either we are some full turn, so either we do sometimes some number times 2 pi, or we do some numbers times pi. So therefore, kappa a must be equal to n times pi in order for sine kappa a to be either here and be 0, or here and be 0. And since we introduced this n here, this gives us a family of kappa values. So we will also add an index n to this kappa to say that it is the index corresponding to this n here. So we can keep track of each element of the family of solutions. So now, if we replace by the expression of kappa, we also add this index n to e, and we get the following equation. Now we will isolate en, and there is this a as well that was here. So we have 2m en over h bar squared is equal to n squared pi squared over a squared. Therefore, en is equal to n squared pi squared h bar squared over 2m a squared. And we see that the allowed energies of the particle in the box is not a continuous set of values. Instead, it is a discrete set of values, and that's why we say that the energies are quantized. Quantized or discretized. They can only be equal to certain values. So now we have computed the possible energies of the particle in the box, and we see that it's some quadratic behavior in n. So the first level will be here, the second level will be here, and the energies become greater and greater, right? The separation between the levels, so if this is E0, this is E1, this is E2, this is E3, the separation becomes greater and greater in terms of energies. So we have these energies, also known as eigenvalues of our problem. We are now looking for the wave functions or the eigenfunctions of our problem. And we already know their expression. So we know that psi, which now we also put this label n to label the families of solution. We know that it's equal to b times sine of kappa n times a. And we are looking for this b term here. To find this term, we use the usual trick of normalizing the wave function. So the integral between minus infinity and infinity of the density, so psi star psi, equals 1, because the wave function should be normalized. Now, this integral is actually an integral between 0 and a, because outside of 0 and a, psi is 0. Then we have b star sine and b sine, so it will give a b squared sine squared kappa n a equals 1. And here, if you remember your trigonometry, we have the usual formula cos a plus b equals cos a cos B minus sine A sine B, and cos A minus B equals cos A cos B plus sine A sine B. So if A equals B, this becomes cos 2A equals cos squared A minus sine squared A. And cos A minus A is 1 equals cos squared A plus sine squared A. Now we want to obtain or isolate this sine squared A, so we do the second line minus the first one. So 1 minus cos 2A equals, so the cos squared cancels, and we have 2 sine squared A. And this gives sine squared A equals 1 minus cos 2A over 2. So coming back to our normalization equation, we have B squared 0A dx 1 minus cos 2 kappa n A over 2 equals 1. And this is a very simple integral. We have B squared, the integral of 1 over 2 between 0 and A is A over 2 minus the integral of cosine 2 kappa n. Oh, it's not A, here it's x. Of 2 kappa n x is simply sine 2 kappa n x over 2 times 2 kappa n between 0 and A. And we know that 2 kappa n sinus of 2 kappa n A will be equal to 0, and sine of 0 will also be 0. So this term in fact is equal to 0. And the whole thing is equal to 1, so we are left with B squared equals 2 over A, and therefore B is equal to square root of 2 over A up to some phase factor, exponential I theta, that we can discard here because it does not influence the results. Finally, we have our full wave function psi n x equals square root of 2 over A sine kappa n x. These are the wave functions or the eigenfunctions of the problem, so the possible states of the particle in the box. And here we draw some of these wave functions. So let's start with the simplest one. The blue curve is the amplitude, so the thing that we just computed. square root of 2 over a times sine kappa n x, and the orange curve is the probability density, so the square, or the norm squared of psi. What we see for the first eigenstate is a symmetric wave function with a peak in the middle. Now, for n equals 2, we see an odd function with respect to the middle, and we see that there is a point where the probability density in the middle is equal to 0. So not only at the boundaries, but also there is a point in the middle where the probability that the particle is there is 0 when the eigenstate is the number 2. And the peaks will be around 0.25 and here around 0.75. Let's continue, and now again we see something symmetric with respect to the middle, and now two places where the probability density is 0, so the particle will not be found here. And it alternates between odd and even wave functions with respect to the middle. And the more we increase the quantum number n, the more places there will be where the particle can have 0 probability of existing. But at the same time, the more the quantum number n increases, the more the wave function oscillates. And it oscillates more and more rapidly, such that in the limit of n very large, we can see that it will oscillate very rapidly between two values, and what will happen is that we will have some kind of uniform distribution. It will be equally probable to find a particle at any position between 0 and a. So recovering some kind of classical behavior. Okay, so there is also some nice property that this particle in a box showcases, and let's recall that any state, any general state, can be decomposed on the basis of eigenfunctions. So these psi n that I call ket n and bra n here, such that we have any state psi written as a sum over n of some coefficient Cn here times some eigenstates of quantum number n. Now, let's imagine that we let this initial state evolve with the Hamiltonian of the problem. What this gives is the following. We replace psi by its development on the eigen functions of the problem. And now we have this operator, this evolution operator, that applies to the eigenfunction n. And since n is an eigenfunction of h, this will give simply exponential minus I en times t. And now let's ask the following question. Is there some time t such that starting from some initial state psi and letting it evolve for this time t, do we get back psi? Is it possible to have some initial state in our particle in the box? So let's imagine some wave function like this that we let evolve so for some time t, so it will do some complicated evolution, but after this time t it comes back to being this same exact state that we started with. Is this possible? Well, it is, and we will see that it's simply a matter of finding the right time t such that the evolved state is equal to the initial state, which was Cn times n, like this, a sum over n of Cn times n. Let's project this over some state k. So if we apply this bra to this equation, what we get is Cn e minus ent delta kn equals Cn delta kn So basically, e to the power minus I n, okay, t equals to 1. So there is a time for which any initial state will come back to being the same form. And this time is given by this equation that we solve. So again, the trigonometric circle, when does exponential minus I something is equal to 1 it's when we are at this point. So either 0, but 0 is not a good time for us here, or 2 pi, or any factor times 2 pi. But 2 pi will do, so ek times t equals 2 pi. So this t must be 2 pi over ek. And this is valid for all k. That is, for every single eigenstates, there is a time that respects this condition here. And this time is called the revival time. It's called a revival time because it's like the initial wave function here evolves and interferes and does complicated stuff. But after this time t, it revives and becomes the exact same as the initial wave function. This is called a revival time. Okay, so now let's ask